very clearly. So let me see. Do I pronounce your name correctly? Davina? Or how do you pronounce? Okay, good. Thank you.
Okay, okay.
Davina. Okay.
Sorry, before we start, I would like to ask you about how this course, would you like to, when there is a question you...
So you can, will people raise their hands, or will they use the chat for questions, or how will they?
Or you start your presentation until end and then they ask, or if there is a question, they just raise hand?
Yes, if they can raise their hands, and you let me know if a hand is raised, because I'm not going to see it. I'm not going to see the participants window. But what I'll do is, once in a while, I may stop and ask, is there a question? No, and then if there's a raised hand, you let me know.
Okay.
And some people, I know some participants, they prefer to enter their questions in the chat. So they can do that. And then at the end, maybe you can read the questions and I will answer.
Okay. Let me begin. Good day. Good morning for Professor Magaly, and good evening for all the participants. Me, Devina Trismanawati, speaking here. I would like to welcome you on the fourth webinar series of the Professor Visiting Program organized by Department of Geological Engineering of Universitas Diponegoro. Today we have Professor Magaly Koch as the presenter here. She is professor from Boston University. Her research interests mainly focus on exploration of groundwater resource, assessment of natural hazard, and land use change impact on water or land resource in arid or semi-arid and tropical environments. From the previous webinar, we have her and she was explaining about fundamental remote sensing. Today we have her to talk about mapping technique using remote sensing. Okay. All right. Before we get started, I will read out about some rules for conducting this webinar. First, during the presentation, the committee will turn off the voice and annotation mode because it will potentially interfere the presentation. And second, if you have any question, please raise hand and the committee will open voice mode, or you can type the question in the chat box. And the last, please turn off your camera as it will help stabilize the bandwidth. Okay, without wasting time, let's listen to the material to be delivered by Prof. Magaly. Prof. Magaly, time is yours.
Thank you very much, Davina. It's a pleasure always, even remotely, even virtually, to communicate and to engage with ONDIP professors, students. Actually, I should say first students and then professors. And so hopefully today's presentation will sort of enhance your interest in remote sensing, and especially as applied to geology. So today we will discuss some mapping techniques. And as Davina already said, last time I talked more about the fundamental aspects of remote sensing. And here this slide is just to remind you that you can also contact me via email at Boston University. And I'm a research faculty in the Center for Remote Sensing, which has been around, I think, since late 80s. So that's 40 years. The center was in the east coast of United States, one of the first remote sensing centers that were created in a university, and remote sensing, satellite remote sensing has been used for the last almost 50 years, half a century. Can you imagine? With Landsat 1, which was launched in 1972. So in 1986, Boston University decided that they wanted to create a center because the infrastructure for using these satellite images and processing the data required huge investments. Computers were very expensive. Actually, PCs were not powerful enough to process these images. We had to use microstations, and the operating system was Unix, so which is nowadays known as Linux. So that was a little bit of a historical background of our center. Nowadays, of course, there are remote sensing centers, I mean, all over in many countries and continents. And the technology is now much more accessible, and even software are now available for free. But this lecture here is going to walk you through some analysis tools. And we will start with the first one, which, as the title says, is called lineaments, right? We geologists are often interested in mapping a region according to the fracture and fault systems, basically which allows us to know about the tectonic framework of the region. And these features, when you analyze them on a picture, on a photograph, could be also an aerial photograph or an image, they're termed, or they're called lineaments, not directly fractures or faults, because they are linear features that the user has to interpret first. So there are two steps. You need to basically identify them, recognize them visually. That means that the image has to be processed in such a way that there is enough contrast and you can clearly see the lineaments. And second, once you trace them and create a map of linear features, the second step is to interpret the nature of these linear features. No? So there are many reasons why these linear elements appear on your image. So fractures and faults is not the only one. It could be also a linear feature demarcating, outlining a geomorphological structure, right? And it's basically the task of a geologist or a student in geology to go to the field and actually do what we call validation, ground truthing. So, and that goes for anything you map on an image. You basically manipulate, process the image to extract visual elements, visual features. But then the next step is the interpretation, right? And I'm often cautioning my students when they use, for example, these scripts that are now made publicly available to run certain algorithms using, for example, Google Earth Engine, right? That's just one example. And there's some tutorials, and then they run, the script, right, with all the functions, the commands, and so on, and they get an output. It could be a classified image, could be something else, but the job is not done. You need to go and validate the output, and you need to know what you mapped. What is it? What's the real nature of that? And that requires field work. So at some point, you need to go and check. In cases where you cannot go because for example, in my case, I'm working in different parts of the world, and it's not, and especially now with COVID-19, it's unfortunately not possible to just take the plane and go somewhere. Well, in that case, you try to contact someone who lives close to this area, and hopefully you establish a collaboration with that colleague, and then let them actually explore the area. You provide the images or the interpreted satellite images to them, and they will then do the validation. So collaboration is usually a common thing, But in any case, so this was kind of an introduction. So we are talking now here about lineaments. So the true nature of such linear elements, may not be known by you while you're trying to process, enhance the image, and extract linear features. So at the beginning, you may not know exactly what they mean, right? And that's why we use this term. It's more neutral. Some of these linear features may be human-made, like roads, like dams, like any infrastructure, right? There are also, some of them are linear, and you may think, oh, maybe this is a natural feature. No, it's a human-made feature, right? But others are, many others are, of course, natural features. So the distinction between human-made linear features and natural features, that's the first step. And you need to train your eye to identify these differences. One thing I can tell you is that human-made features, linear features, they tend to be very geometrical. They follow a pattern, a geometric pattern, usually, not always, right? And natural features, they also may show a very straight line, but eventually you see that they're interrupted, or they're not following really geometrical patterns. So digital image processing is the software we use to detect these linear features, identify them, map them, and then of course validate them. And the procedure to enhance your image so that you can do the mapping either by doing on-screen, digitizing, or there are also automated ways to extract the linear features. So the process of enhancing your image to be ready to carry out that procedure is called edge enhancement. Edge meaning the boundary between two things, right? Or sharpening. And the next slides will illustrate how spatial filters work in remotely sensed images. So we call them spatial filters. What is a spatial filter? Well, the word spatial tells you that it got to be something that is sort of distributed somewhere, or shows a pattern, a spatial pattern, right? In digital image processing, spatial filtering functions, they have the goal to enhance the appearance of an image, to make them the contrast much clearer, to sharpen the image, to reveal details, because sometimes these linear features, they're on your image, but not so visible. So you've got to somehow make them much more visible, and we do that by applying contrast. Contrast, as I said, along the edge, the boundary, because remember that, and I mentioned that last time, the computer itself, the algorithm, works with numbers, digital numbers. The program doesn't actually look at an image. We need to visualize the information because we use our eyes to see the results, but the computer program uses digital numbers. And so for for a machine, it's very easy to differentiate between two different tones or brightness levels, because it just needs to detect the difference in the digital number. However, when you visualize the image, for your eyes, it's sometimes very hard to distinguish two different gray tones or two different brightness tones, because our eyes, they don't have a very high, what we call a high radiometric resolution, right? We're not capable of differentiating, seeing so many variations. So this is also one reason why we like to look at color images, because our eyes are much better in detecting nuances, variations in color than in black and white or gray. We're not good with gray, tones. So back to the filtering and spatial filtering, which is different from spectral filters, right? So here we have a picture. It's actually sort of it's not even a scene. It's just an artificial image. And we see that on the left, it's actually in color because we're better in seeing different nuances, shades of color than black and white. We see that the upper left corner is dark green, and as we move slowly to the opposite corner, it becomes brighter and eventually it's white. And this gradual change in tonal variation is called low frequency features. Low frequency means that the type of variation is very gradual, right? Whereas on the right side, we see a checkboard pattern, and it's basically only two colors, black and white, right? But the variation occurs at a very, very short distance from one pixel to the other. Whereas on the left side, it occurs gradually, and it takes, sort of some distance to show the variation. So the right-hand side picture is called a high frequency feature. And so this is very abstract. These are artificial images. They're not real, case images, but we can translate that to our satellite images. So when we see a landscape where sort of the different geomorphological features, are vary or they change gradually. That's called the low frequency landscape. High frequency would be when you see abrupt changes, like, for example, rocky mountain area with cliffs, and then all of a sudden, you got the top of the cliff, and then there's a sharp boundary, which is the cliff, face, and then the bottom, and they are made up of different rock types, and so basically within the short distance you have a lot of variation. That would be high frequency. Okay. Other words that you can use is, for example, rough texture. Would be this one here, and smooth texture would be on the left. Spectral filters are different. Spectral filters are, for example, our sunglasses, right? They protect us from UV radiation, and they eliminate some type of radiation, but not to be confused with spatial filtering. Okay, in geology, remote sensing geology, we like to use spatial filtering a lot. You will see why. Is there a question here? Just please let me know. Okay, so I will proceed. And here we have an example. It's a black and white image because it's only one single spectral band. These filtering operations, which are called also image convolution, they operate on a single band. That doesn't mean that we cannot, apply them to all or a number of spectral bands. And actually, our computers do that nowadays simultaneously. Parallel. They run these processes parallel. But we're looking at one example and how it works. And the operation is actually what we call a local operation that modifies each pixel according to the neighboring pixels. And the way it's done, so this image here is represented here in an abstract form. And you can see that each pixel has a brightness value or a color or a gray shade. And then we place an algorithm. This is the algorithm that contains, or it's called also a kernel, that contains a number of cells, right? So it has a dimension. We place it on, usually it starts at the upper left corner on the image, and then it will consider all the pixels under it and run an algorithm, a mathematical operation. And this mathematical operation, I will show you in a minute how it works, will modify the central pixel. So the kernel usually contains an uneven number of cells and rows because it got to have a central cell or pixel, right? Because that's the one that is going to be modified according to the neighboring pixels. So it applies a mathematical calculation using the pixel under that window or kernel and replaces the central pixel with the new value. And what's the outcome? Well, the outcome is to actually modify the central pixel either by sort of making it darker or lighter and enhancing the contrast between the central pixel and the surrounding, right? I've mentioned that for edge detection or linear feature detection, contrast is very important because our eyes, they need to see very contrasting colors or gray shades. Otherwise, we will not recognize much. And after it finished this operation, the first one, the kernel is moved along the row to the next couple of set of pixels and performs the same operation again. Now, the kernel itself can contain what we call weighting factors. So is there a question? Shall I continue? Okay, let me know. Should I continue? Okay. Yes. So this procedure is further explained here in the next. Let me see. Next. Okay. Slowly but surely. Okay, step by step. So we got now our image. It's now a reduced size. And instead of seeing brightness, colors, or gray shades, we're looking at numbers because that's what the computer codes are, right? These are digital. Your image is basically a numerical matrix. Okay, this is our image, and the low numbers means very dark colors, and the high numbers mean very light colors or bright. And this is the kernel. Now the kernel has a specific size, and the size has to be, needs to use uneven, numbers, because we need always one central cell. Now, it also contains coefficient or weighting factors, and in this case, the weighting factor is 1, but it can be modified by the user. No? And so we're going to place this on top of our image. And our first target pixel that we are going to modify is this one here. Why? Because it has to have surrounding pixels. It cannot be this one here in the upper left corner or even along the edge. Why? Because it wouldn't have surrounding on the left side, a neighboring pixel. So it got to be the first pixel that can be modified in an image needs to have surrounding pixels according to the kernel size, because the kernel needs to fit exactly on the images or image values. And now, how do we modify these values? You see that, well, there's some variations. So between 2 and 3 and 3 and 4 and 1 and 3 and so on. And these two, they don't show any variations, right? So how do we modify the target pixel or central pixel? Well, we need to apply an algorithm. And the algorithm is shown here. So it's basically the sum of the kernel values multiplied by the image neighborhood, and then you take the sum and then divide that by the sum of the kernel. And mathematically, it's explained here. So you place the kernel on top of your images here, and you carry out a simple multiplication, right? Remember that these three have the same value, whereas the other ones have different values. So after carrying out the multiplication, you will sum all the products and then divide them by the number of kernel cells, which is 9. And then you get, you basically divide it and get a value that is usually a floating point value. So the original pixel value 3 is now going to adopt the new value 2.56. And you do that pixel by pixel. You move the kernel to the next, set of, or to the next cell on the same row and carry out the operation. And then once you're finished with one row, you move the kernel down a column and do again the same operation. Okay, very simple. Any questions here?
Yes.
Yep. Any questions?
Not yet.
Not yet. Okay, thank you. I'm just checking. Okay, so the last slide was just to explain the procedure. Now, of course, there are many types of filters, because here you have the opportunity, when you look at the kernel, you can actually, as the user, you can decide which values the kernel should adopt. Remember that these values, whatever these values are, and they don't have to be equal. You don't have to use the same value for all the cells. These values will be multiplied by the image digital number values. So by designing, and it's called designing a kernel, you should take into consideration the purpose of your filtering operation. Whether you want to, what is it exactly you want to do? Do you want to average your image digital values and sort of apply a median filter? Where basically you do the opposite of sharpening. You blur the image, right? Or do you want to do use a filter where you enhance edges, right? And this is what's done here. So in this case, we're going to try to enhance linear features that are contained in your image. So if you look at my image here, it consists of actually only two values. It's done for simplicity reasons. I can see only cells that contain either the value of 25 or 30, right? No other values appear, absolutely no other values. However, for our eyes, it's very hard to see a pattern, although there is a pattern. And the pattern is indicated by these arrows, right? If you follow the arrow direction, you see that all the values along this line have the same value of 30. And if you follow the pattern along this line, sorry, it's my mouse is not responding very well. All the values are 30, and the rest of the values are 25. Now, for us to pick up this pattern is hard because we're looking at numbers. We're much better at looking at the color. Now, if we would trace a line between A and B, and we would plot the values, how they change along this line in a graph, and that's done here, right? We would see that along the AB line, most values are 25, right? So basically the line is flat. And then all of a sudden, there's a jump to 30, and then it goes down, flat, 25, and then it goes up, and so on. And these are where it goes up. These are our either northwest or northeast trending lineaments that are hard to see, and we need to enhance the contrast, basically the difference between the surrounding pixel values and the lineament value. And that was done in this next picture here. Now we basically we're looking only at one set of lineaments, the northeast trending lineaments, and we designed a kernel that would only enhance those type of features. I mean, the contrast of those type of features. No? So our other northwest trending lineament still has the same value of 30. Only the one basically trending or striking in that northeast direction have been increased to 50. But not only that, the pixel before the lineament pixel, both sides, the values have been lowered. They're not, they also have been modified, and this is shown here. So before the lineament and after the lineament, those pixel values are no longer 25. They're now, I think, what is it? 15, right? And the lineament pixels has a value of 35. And we can do that also with the other northwest trending lineament. Okay, so in other words, what we're doing here is we are enhancing the contrast along linear features. And by doing that, we are also modifying the width of the linear feature. Originally, the width was maybe only 1 pixel, right? Here the pixel number. And now the width is 3 pixels. No? And this is this helps our human visual system, our eyes, to identify the features because now they're wider, right? Now we can see them, right? And here are some examples. So on the left, we have an image of Bighorn in Wyoming, Bighorn Basin in Wyoming in United States, and actually northwest United States, and it's an arid environment. I will show you this picture. Hopefully, we'll have time for a demo, and I prepared the image, so I'll show you with the software that I use. how it looks in color. But what's important here, this is just one band. You can see a river, a meandering river. I hope you can see the black line that sort of meanders here. That's a river, and it's right along the river. You see agricultural areas. They're very bright. Why? Because vegetation reflects a lot of light in near infrared and also in shortwave infrared. And this is a shortwave infrared image. So that's why vegetation looks very, very bright. Whereas the rocky surface, these are sedimentary, layers, they have different gray shades and they're a little bit darker, right? And there are some linear features you can see here, right? And here's another one, right? And this river probably follows, not probably, I'm sure, follows a fracture zone. And not surprisingly, the river is actually taking advantage of this weakness zone in the earth crust. It follows the fractures, and you can see how the intersection between this river and the other is perpendicular, right? And these are synclinal or anticlinal systems, right? And you see the outcrop of the sedimentary layers, right? So let's say you are interested in mapping particular linear features, right? Doesn't have to be only tectonic features. Could also be geomorphological features, or or even you may be interested in detecting man-made features like agriculture boundaries, field boundaries. So you can design your filter to perform a certain task. And this one is called a Sobel filter. It kind of is an edge detection filter, and it works for any type of linear feature, whether even for actually not only linear feature, also for round features. For example, this is an irrigated field, a round field, and it detected very well the edge of the round field. So this is a filter that really detects any edges, whether they're curved or linear, right? And it also, as you can see, it draws a boundary, and the boundary is quite thick, right? So it makes it easier for you to pick up. And it suppresses anything which is not an edge or a boundary. It's going to be dark to introduce contrast. And so you could then go ahead, use this product, use another algorithm to extract only very light pixels, and then you end up with a map showing these curved or linear features. The other, or the next picture here shows you a filter that has the goal to suppress edges, the opposite. So this filter does the opposite of this one here. This filter, remember when I was talking about high frequency and low frequency? This filter is good to extract high frequency features, right? Very busy. It looks very busy, the image. This filter is good to enhance low frequency features. It basically suppresses, high frequency features. Why would I carry out, or why would I apply an averaging filter? Can you imagine any reasons for geologists to actually produce an image that looks like this, very blurred? The edges are very blurred. Can you imagine why you would do that? Any idea? Use your imagination. I know there are many chats, but I'm not sure if someone is asking a question. Okay, well, it could be that you are not necessarily interested, in mapping boundaries. You are maybe interested in mapping color variations of the rocks and the lithology, not the boundary itself. but you want to see if there are certain what type of lithology exists, or if there are some, variations. Could be also the soil. Doesn't have to be only the rocks. And by de-emphasizing the linear feature, you're focusing more on the color variation, and you're looking for homogeneous areas with the same gray shades. And I can see here, for example, here's a dark spot, dark patch, and this is lighter. I can be sure that this is probably sort of a different rock formation, or maybe, the weathering material is different, but there is there are like two different types of rock units there. And also here, I can see that very clearly, the banding. Remember, the banding of these sedimentary layers are difficult to see, because here we only see the edges, but here we see the color variation. So that would be a reason for using this type of filter. And another task you may want to perform is, okay, I'm actually interested in mapping only linear features that strike in a certain direction. So this is called a directional filter, and that was done here. So this filter uses a kernel that will highlight the contrast between features that are aligned in 45-degree direction. So especially this river system here. And it de-emphasizes the opposite, perpendicular direction. Remember here, this northwest southeast trending linear feature or banding is suppressed. It doesn't show up very well. Whereas here it shows up very well. You can see it very well. And this direction is kind of suppressed, right? So it allows us to look at the fabric of our landscape by focusing on not only, let's say, edges, but also the opposite of edges. Basically, you want to remove edges. You just want to focus your attention on, contrasting surface material, or you want to focus on linear features or edges in certain directions. And all these products can be used together to basically map an area according to its framework. And here are a few examples. They are actually taken from a textbook. And I think this is the picture, basically a section of a Landsat TM Band 5 picture of a part region in central Ethiopian rift. And you see here a lake in dark. You see some rivers. This is a river, right? And you can see also some darker spots here, which are supposed to be marsh, wetland. And then definitely linearity in north, east, southwest direction. And this image was enhanced and then mapped. And whoever mapped this, I did not do this. This is taken from a book. They interpreted these lineaments, and for example, they gave the different lines different thicknesses. So, for example, the lake, the shoreline is thicker than the tensional rift faults, and you can see that they may have not included all lineaments here. For example, the river is not included because this map is supposed to show mainly tensional rift faults. So you can, after you carry out your filtering and all that, you need to interpret the nature of these linear features, and then you can basically produce maps that show certain type of linear features. Another example, they used a high-pass filter. High-pass is another word, another term for high frequency. So high frequency filters and high pass filters are more or less the same. And here again, it's a lake in central Ethiopian Rift Valley. And the lake water is very dark because this is probably a shortwave infrared picture. And water doesn't reflect light in shortwave infrared. And you can see that they use the filter. It's the quality is not very good, but it looks very busy here, right? And you can see that the color of the lake and the land is the same. Great. So this filter basically suppressed totally the contrast between land and water. There's no contrast anymore because land and water have the same gray color, but they enhanced the linear features. And then they did an interpretation based on this picture here. And of course, probably they had some additional maps, or they went to the field, or they did some checking. And what they show here is that some lines are thinner and apparently dashed, and others they're thicker. And the lineaments, the thin ones, they probably show fractures, no? And the thicker one, according to the explanation here, they show the former shorelines of this Lake Shala during the Pleistocene expansion stage, no? So they did an interpretation of these lineaments, okay? And here are some other examples. And you can clearly see how the original image has been processed in such a way that different levels of or details show up, no? And I think these are also showing different directions or emphasizing different directions. And this is a granite area in this time in India, of a little weathered terrain. Okay, now lineament extraction is certainly one, one of our goals in producing, eventually producing a tectonic map, for example. But it's not the only one. No, there are many other landscape or landform features we want to enhance. And another technique called data fusion is very popular because it allows us to combine images from different types of sensors, for example, radar and multispectral images. Last time I gave you, my last lecture, I gave you an example of the Sinai Peninsula. Remember, we fused basically a RadarSat image with a Landsat multispectral image. And here I just want to show you the technique a little bit. Why would we do this type of multi-sensor fusion? Well, because each type of sensor that operates in different regions of the spectrum may contain complementary information, which may highlight different aspects of the landforms and rocks. So what's important before you do the data fusion, you need to prepare the data, because the data was imaged by using different sensors. So the dimensions of the images may be slightly different. You need to make sure that they have the same geometric properties. So the geocoding is the same. You need to make sure that the pixel size is the same, the coordinate system is the same, because you're going to basically, drape over two different data sets, and they have to match, they have to be aligned. No? So with radar, we have the additional problem that in very hilly terrains, there's a lot of distortion, and you need to run a terrain correction algorithm. And for that, you need a very good, excellent digital elevation model, so that you can place the radar pixel into the proper flat planimetric position, because there's a lot of, with radar, a lot of relief distortion. So you have to flatten the radar pixel, right, before you do the fusion. You know? That has to do with the fact that radar is side looking. It's not looking down, it's looking, you know, sideward, and there's a lot of distortion. Whereas with Landsat, it's a sensor that is looking down, and the distortion is less. They also need to be, you know, pre-processed, and you know, distortions have to be eliminated. But with radar, it's the process is much more complex. So here another example from this time from one of my research projects in Egypt, in an area west of Aswan. Aswan is the city, you know, next to the Aswan Dam, Lake Nasser. And the river, the Nile River, is seen here, very dark in red. This is because we applied the contrast in such a way that the very, very bright desert area doesn't look so bright. So that darkened the Nile Valley. And we were interested in mapping actually features here within this desert plain. And this is an escarpment. You see the boundary very clearly. And these rocks, this is a plateau. These rocks are limestone. And there's a cliff, there's a very, you know, this is high and this is low. And so we wanted to create a classified image showing us some variations within the sandy, flat area. To the naked eye, it looks all the same. You go there and, you know, you don't see much variation. But the mineral content of the sands, and also the grain size of the sand varies, it changes. So the sand is not homogeneous because there's some wind-blown sand deposited on the surface, and they form these linear dunes. This is a dune, by the way. And then there are these alluvial, you know, plains and alluvial fans, and the mineral content is completely different from this one. Here you have more silica, and here you have more clay and clay sediments. You know? And so we wanted to sort of create a map that would show us these variations. In this case, we're not so interested in linear features, but we are interested in texture, because texture can tell you something about the position of the sand. You know? Some of these sands were deposited by ancient rivers. They're no longer flowing through this area, through this plain, but in previous geological time, this was an alluvial, you know, a delta, actually a delta system. But on top of the delta sediments, now there's wind-blown sand, right? And the radar can penetrate a little bit this wind-blown sand and can reveal certain features that are more difficult to see here. If you look at the, oh, by the way, this is the River Nile, and here you can clearly see the River Nile, no? If you look at this feature here, so this is a pulsar image, you may see these breaks in the rock, right? They're also here, but less clear, no? So by fusing both and then running classification, we were able to separate certain units, no? And that, of course, helped a lot when in understanding the positional and erosive you know, history of this area, right? And by the way, the radar shows these very, very straight lines. Any idea what this might be? I don't know if you can see it, but these are man-made features. They're also very visible here. They are, and they're also visible here. So those would be artificial, you know, linear features. Another example from Jordan, And this is not, it's not from any of my research projects. It's also taken from another source. And here what they did is they combined Radarsat with Landsat, but before that they processed Landsat in such a way that it would create these very colorful, you know, landscape variation. And here's the legend. And basically you see here in blue and purple colors, the agricultural fields in the flats. And then this more rough texture here are mostly limestone, right? And then on top of it, you see some aeolian sediments were shown, I think, in what is the in E? Yeah, E. Okay, basically this area here. And then you see also very dark color basalt, and also very clearly some structural features, no? And the drainage pattern is following some of these structural features. So another reason for doing not only a color you know, enhancement, but also textural enhancement, and doing that using a combination of radar image with optical multispectral images. Okay, any questions so far? Let me see time-wise how we're going. All right, that's fast. The next slides are just to summarize how these images were fused, right? There is a procedure called intensity, hue, and saturation transform, and it's based on the color model. You know, these images, they're very colorful, so usually we use the RGB color model to visualize these images in red, green, and blue. But there's another color model, hue, saturation, and intensity, which is used in data fusion. And the reason, and actually you can convert an RGB color, I mean an image shown in RGB color, you can convert that to intensity, hue, saturation, and vice versa. So these two color models, they basically describe you know, the same thing, the colors, just they're using different properties of color, you know? And there are mathematical functions where you can convert an image from shown in one color model to the other and vice versa. But the advantage of the intensity, hue, and saturation color model is it has a band or a channel that contains the intensity information of the image. And intensity, the definition of intensity is it represents the brightness values and brightness variation, right? And brightness variation, this is something very important in edge detection and also in filtering. Remember the previous slides and all the examples I gave you. These algorithms, what they did is basically they changed the brightness variation along the edges, right? So if we can somehow, you know, replace the intensity channel or information in an image by a higher spatial resolution image, and then transform everything back to the RGB, we have a way of combining the multispectral information from, for example, from Landsat with the pachromatic information from, you know, a higher spatial resolution band. And that's what's being done using this model. Here, just a graphical way to describe both models. The RGB, so basically the axis represent the three primary colors, and all the colors can be described by using these three primary colors. We have another model that also describes all the colors, but it used this cylinder where you have the hue, the color represented along the perimeter here. Then you have the saturation. Saturation means, you know, how much, you know, how pale is an image, color, or how how pure is a color. That's the word I was looking for. So the color becomes very pure towards the perimeter and less pure towards the center. No? And then intensity would be the brightness variation. Okay, so the IHS transform is useful in two ways. It can actually also be used to enhance the color in an image, you know, and make it very vivid. Or it can be used to actually perform a data fusion. You know? And here are the 4 steps that need to be carried out. You need to register, you need to register your high resolution image, usually a panchromatic band, and your lower spatial resolution image, which is a multispectral image, and then you convert the TM, the Landsat, the multispectral image from RGB to IHS coordinates. You do that with an algorithm, and then once that image is in IHS coordinates, you substitute the pan band for the intensity coordinate, and then you convert it back. So this is not the, you know, very important to understand. It's just for those who already have some notion and have done some data fusion, just a summary of how this is performed. What you need to know basically is that after you fuse your images, you gain the best from both data sets. You gain the color, the spectral, you know, color from the Landsat, and you gain the textural information from the radar. And that allows you to do a much better interpretation of features. Okay, and then the other set of processing I wanted to describe here briefly, and I will give an example, is called spectral ratioing. Okay, and it's very simple. It's basically the process of dividing the pixels in one image or one band by the corresponding pixels in the second image or second band. Right? So it's basically applying a mathematical operation. You know? But it has very important, very important impact on the image visual quality, because it can enhance certain spectral features. And I'm giving here an example by showing you the spectral curve, basically the spectral response pattern of vegetation. Remember that vegetation has a peak value, usually in the green wavelength. No, that's why we see vegetation green. It absorbs red. So green would be here, that's the peak, and it absorbs red, and then it shows a lot of radiation or reflectance in the near infrared. And this slope here, this slope from the near infrared to red, is called the red edge. And that slope contains a lot of information about the condition of vegetation. When the vegetation is at its peak, growing season, usually the slope is very steep. Let me get some water. I'm losing my voice. And towards maturity, and when the vegetation starts to decay and so on, that slope tends to be flat. So if there's a way we can use these just 2 bands and carry out a division and create a new band, just a single band showing the slope information of vegetation, we have a way of saying whether in which stage the vegetation is, whether it's in a healthy stage or maybe it's in a decadent stage. But this is not only a technique that works with vegetation. It also works with soil and rocks. You know? Because when we look at the spectral pattern of, for example, white soil or basalt, again, we have here the wavelength and here the reflectance or radiance. And the curve will tell us in which spectral region this material, you know, reflects light or absorbs light. And you can see that with basalt, it looks very flat. It looks, you know, almost featureless. With white soil, we can see it has quite high reflectance values, probably here in the visible and near infrared, and then it goes down towards the shortwave infrared. So if we can sort of select two spectral bands, and they are shown in bars, two spectral bands that represent spectral regions with very different you know, behaviors, spectral behaviors of this type of material, white soil. Let's say band 4, and this is, I think, band 7. And you can see they have very different values. If we take those two only, those two, and divide them, then the output will be one band showing the slope. And that slope can be used to highlight lithological you know, units. So I'm going to give you an example, and it's going to be based on certain ratios. This is Landsat TM, and by you know, sort of observation and basically empirical studies, we have been you know, observing that certain ratios of bands are good for highlighting certain types of minerals or sediments, right? That doesn't mean that if you create that ratio, let's say band 5 and band 7, that, you know, it's going to highlight always clays and carbonates. It only works for those images that actually show an area that contains clays and carbonates. So if there are no clays and carbonates in your image, you know, it's, even if band, this ratio of band 5/7 highlights certain features, it's probably not going to be clays and carbonates, okay? Why is that? Why is it certain ratios highlight certain types of rocks? So again, we need to look at the wavelengths here, down here. And in laboratory experiments, we can obtain spectral response pattern for each of these types of minerals, right? And we can then take a note or record in which spectral regions do they tend to have their peak reflectance. For example, with ferric oxide minerals, they tend to have their peak reflectance values in the visible, right? With carbonates, it's going to be more in the short wave infrared. And clay minerals, they have certain regions here, no? And then based on this behavior that we can obtain from laboratory experiments, we can then now assign or map which bands of our sensors, you know, are more appropriate to highlight these different minerals, okay? So I wanna do this, actually in, let me see how much time I have. Okay. Are there any questions so far? I'm going to give a demo, but just want to go quickly over these slides. Just
actually, there is one question from
okay.
Franz Tony, but it's not included to your material. He asked about how to make a topographic map from Landsat imagery. And then could you
what type of map? What type of map?
graphic map.
From Landsat?
Yes, from Landsat imagery. Is it possible?
No, because Landsat images, they contain spectral information and they're not in stereo, right? So for topographic maps, I suppose that they're referring to digital elevation models, right?
Yeah.
You need a pair of images, a stereo pair, or you need to use radar, but not multispectral bands.
Okay. There's only one question. As
Okay.
You can continue. You still have 30 minutes.
How much time?
30 minutes to present it and 30 minutes for question. So you totally have 1 hour left.
Okay, thank you. Okay, so yeah, I wanted just to show these spectral curves because they're important for what we just discussed, the ratios. And again, some examples. This would be visible light and shortwave infrared and so on. And you can see with these 3 colors, they represent in green typical vegetation spectral curve or signature. In white, this is talc mineral. And let me change the pointer. This is talc, completely different from vegetation. No? It doesn't have so many dips and valleys, but it has certain dips, and they're very narrow and in very specific places. So if we would have a spectral band that records this information, then we would have a way of maybe detecting this mineral. And then silty loam, right? Also different. This information here was obtained from a laboratory measurement, and the curves are very well defined, you know, very well. This graph here shows the same 3 materials, basically vegetation, soil, and you know, a mineral, but using the Landsat bands, right? And Landsat only has 6 bands, so that's why the curve is no longer curve. It's actually, you know, there are 6 points connected by lines, but the shape, as you can see, all these 3 have different shapes. No, they're clearly can be clearly separated. And this one was obtained from an airborne hyperspectral sensor. And there are some gaps where the airborne sensor doesn't have its, you know, it doesn't have bands, right? Okay. So before we go there, I want to give you a demo for to show you how the spectral ratioing work using the Bighorn Basin image from Wyoming. And we're going to create the 5.7, 5.1, and 3.1. Let me see if I can. Oh, okay. I have a software. It's actually a commercial software called Envy. But you can do this also with freely available software. For example, QGIS or Quantum GIS, and there are other software that are freely available because this is a very simple function, no? And most GIS will also have this function. So here we have, remember the image I was showing you in my slides? So that's the same image I showed you here, right? Except that here we see only one band, black and white. So I'm showing you the same image here. Okay. And what I'm showing you here, let me make it a little bit, all right, is a natural, this is, I think, natural color. Yes, natural color. I can see it here because I see the wavelength and I see the color assigned to each wavelength. So this is natural. This is how you would, if you would fly over this area, you would see from the airplane probably the landscape like this. I know the green agriculture area looks very dark, but this is because of the contrast. They wanted to apply a contrast so that you can still see the very bright, rocky area. And you see the banding and you see the structures and all that. Now, if we want to create a ratio image, and I can actually also show you this in false color combination. So we usually, with sediments, in rocky areas, we like to use some of the shortwave infrared bands, either 5 or 7, and then maybe band 4, which is the one that sort of shows agriculture, because it's near infrared in green, and then band 2 in blue. So this is false color. This is a false color combination. This is a natural color combination because we're assigning the monitor channel color to the correct wavelength. Here we're not doing that. We're arbitrarily assigning colors, and you see how now vegetation shows up very clearly, the river shows up very clearly, and so on, right? And another combination, I think it's 7. I think it's 4. Let me see if that works. Yeah, that's another combination. And now vegetation is shown in red. Okay, but back to our bands, and let me just show you one band, one single band, 5. All right, I need to enhance it. Usually you need to apply a stretch. Okay. All right, so we're going to create a band ratio, and I said the first one was 5 as the numerator, and I believe, if I'm not mistaken, go back here, what my 5 7 first, and then 5 1. So numerator 5, and then 7 is the denominator, and I enter the pair, right? And the other one was, yeah, I can say also 3 first, and then 1 is the numerator, enter the other one, and then 5 over 1, and enter. So now I got, basically I'm combining different bands, or always 2 bands, by dividing them and creating a new output which will contain the division of one band over the other, right? Or one band by the other. And I click OK. And now I wanna, actually I'm going to visualize the results in memory. I don't need, and you see it's going to give me a floating point. Why? Because the output of a division, even if the inputs are integers, the output will be a decimal number. And that's what we get. So we get a very, very, let me enhance this a little bit. Sort of grainy, picture. The lineaments are not so clear anymore, but the different color shades are very, very clear. And remember when I was saying that this part of this landscape seems to be occupied by a different type of rock than this here? You see that clearly. And here you can see the boundary, not because you see the lineament very clearly, but you see the color contrast of different rock types, no? And you can of course, change the combination. So these are no longer spectral bands. These are a combination of 2 bands in one. And I can change that. Some people, you know, prefer certain types of colors or color combination. So here I can assign, let's say I want to assign this red, this is going to be green, and this is going to be blue. So the same set of ratios, but I'm assigning a different color to see if it works best. So for example, for me, this color combination works best because the other one, I'm not very good in differentiating red tones. No, for some people, they may prefer the red tones and the green. I prefer this one here. No, but again, it's up to you, right? But you see the difference, no? Here we have just the black and white 1 band, and here we have a combination. If you want, we're here looking at the output of 4 different bands, because we use for creating the ratio, yeah, this is okay. We used band 3, band 1, so 2, band 5, 3, and band 7. So here we have the output of 4 bands. So basically the content, the color content is expressing also the mineral, not only mineral, but the chemical composition of the materials. And even within, I don't know if you noticed that, within the agriculture area, I can enlarge it a little bit, I see some differences now. Now I see different fields, right? Before, they were also there, but less clear, right? This one highlights the differences within the agriculture, you see? So this one is using, it's a false color composite using only 3 bands, and this one is using 4 different bands. You know? And then, of course, if you compare this one with natural, the natural, nope, sorry, cancel. All right, natural would be, so blue is, sorry. Let me see if that looks okay. That's natural. Natural colors. You don't see much compared to this. Okay. All right, so this was the demo I wanted to give you. Of course, if we have later a bit of time, I can show you more, but let's just finish these slides. This is just to show you how these campaigns are performed, because you know, we need to validate the spectral information in the images. We need to collect what we call spectral libraries. We need to know how different features of the landscape, how they reflect light. How do we do that? Well, we can do it, of course, in the laboratory, but that means we need to take samples back to the laboratory, soil samples, vegetation samples, rock samples, and then you know, use a spectrometer to understand how these samples reflect light, right? But that's only giving us the information of small, you know, areas, because the samples come from, you know, tiny areas, and doesn't give us the picture of the whole landscape, right? So the scale is also an issue. And that's why these validation campaigns are also carried out from using an airborne system, because then you can actually get information over the landscape. And this is one of the sensors. You can see it here. This is the hyperspectral sensor dice. And it actually contains not just one spectrometer, but actually 4 of them. And the spatial resolution is 5 meters, and the swath width. So when the aircraft, scans the landscape, the different strips are 3 kilometers wide, right? And the spectrometer has many bands, and here are the bands, and so on. And the bands are not placed arbitrarily somewhere in the spectral regions. You can see how they are distributed. Here we have visible light with 32 bands. Then there are no bands here because there's a lot of absorption happening in the atmosphere. Then we got 8 bands here in the shortwave infrared, and also here 32. So this is the location of these hyperspectral bands along the solar spectrum. And the airborne campaign is usually carried out simultaneously with the field campaign, right? So we want to sort of, compare spectral signatures obtained from the aircraft with those obtained from the field. And in the field, we take a field spectrometer, right? And you can see there's a pistol here, and it's taking a radiation reflectance measurement of a tiny area on the ground. And there's a panel with a very high reflective surface, and this is used to calibrate. Each time before you take a reading, you need to calibrate this sensor here so that you can compare various readings. And basically what you're looking at and measuring are small areas, very small areas of soil. This is a salt crust. This is actually I'm standing here in the middle of a lake, of a dry lake in Spain, and it's in the summertime, so there's no water, but it's a salt crust here. And then after you collect these observations, you can build a spectral library, which we did here, based on this spectrometer. And once you have a library, you can run an algorithm that will use the library as a reference vector and compare it to spectral measurements obtained from the image. And that's called spectral curve matching, right? So here we got 2 colors in black. This line is coming from a spectral library, and we know the identity of that black line. It's kaolinite mineral. And then the red line or curve comes from an image, and you can see that the label says nothing. It says XY. Actually, the label only indicates the position of the pixel. So these are pixel values across the different wavelengths. And by doing this spectral matching, we can see that both seem to have similar shapes. So chances are that both represent the same thing, except that the black curve was obtained from carrying out a field campaign or some laboratory measurements, and the red curve was extracted from a Landsat image. Well, not a Landsat because it has a high spectral resolution from a hyperspectral image. And here just some examples across scale. So we're looking at the spectral pattern of basically the same feature using different instruments, Landsat, airborne hyperspectral, and this would be the field spectrometer, right? And the spatial resolution changes from a pixel of 30 by 30 meter to a pixel of 5 by 5 to an area of 10 by 10 centimeters, right? But these points indicate the same location, and we know that because we use the GPS, right? And these were the spectral curves that were extracted, And you can see for each sensor, of course, the definition of the curve varies. Landsat has a less defined curve, hyperspectral a better defined curve, and the field spectrometer a much better defined curve because it has even some features here in the middle, which are not available here. Here, this straight line means that this sensor did not record any values here. But the shape is similar, right? So if we do the spectral matching, across scale, we will see that all three more or less show the same thing, which is sort of a salt crust of a marshland or wetland. And this is another example, just to show you how across sensor, across spectral resolution and spatial resolution. So we are changing the scale, we're changing the spectral resolution, but the points are the same, the location is the same. No? How these curves somehow show some similarity. And that concept is very important because it means that if we have a spectral library that shows us the different soil types, minerals, and so on, very well defined because they were collected in the field or maybe by an airborne hyperspectral, we can use these signatures as reference signatures, right? To understand and to label the signatures we obtain from a Landsat scene, right? That's called spectral matching. So an image in itself contains, of course, many spatial information, but it also contains spectral information. So by extracting the information from one single point that doesn't show any spatial information, but by looking at the spectral pattern, we can say what type of material it is, because we can compare it with laboratory spectral curves that have been labeled. And the labeling is done the following way. So first you go to the field with your field spectrometer, you take a reading, and you take a reading, not just one. You take a reading of, for example, of this dry or arid, semi-arid wetland area. You take a reading at several spots, and you get a variation of the same soil type, but depending on the salinity level, the spectral information will vary. Okay, from very slightly saline soils to strongly saline soils. And after you do this, you take these measurements, you also take samples. You take them back to the laboratory and you start running all kinds of analysis just to understand the composition of your soil, texture, color, organic matter, and so on. And you can use this information from the samples to better understand the spectral pattern of soil B, moderate saline, corresponds to this description here. And that's called a spectral library built with field data. And this is very time consuming to do this, right? But many agencies, for example, the US Geological Agency has done this. And we can use this information later, I'm going to skip this, to do what we call spectral curve matching. So one of the curves here may come from the image, and the other curve may come from a spectral library. And you can see that the shape is similar, but not identical. And we can use an algorithm to basically evaluate the level of matching, spectral matching. And that's done with the spectral angle mapper. So this is a method. I'm not going to go into too much detail here. I'm going to show you the output, but just very briefly, it's based on estimating the spectral similarity of an unknown pixel somewhere in your image with a reference spectrum. So this reading here, this is a spectral space, by the way. Band B and band A represents not the spatial dimension, but the spectral dimension. So we know what this reference spectrum is. Let me change the pointer here. We know the identity of this one. We don't know the identity of this pixel here, but we can have a way to measure the angle by using an algorithm. And that was done here. So here we have an image. We used a reference spectrum to identify which pixels in this image correspond to Caroline, right? And that was done with this principle of spectral angle measurement. Okay, so this is a method that automatically compares image spectra to individual spectra from a spectral library, does the matching, and depending on you, the user, you can set the angle and say, well, the angle has to be very, very narrow. And if that's the case, then that pixel will be labeled as whatever the reference spectrum is. And at the end, you can then create a mineral map by using the spectral library curves or signatures to identify in your image which pixels have a similar spectral response pattern to one of these minerals. And then basically you only highlight those pixels that have a very, very narrow, very small angle with respect to one of these spectral library curves. And the colors are, they match. So the green color here, whatever it is, muscovite, is supposed to be all these green pixels and so on, right? And that's a type of classification where it's targeted. So you can see that the black means that these pixel areas, these pixels here, they have not been classified because there's no spectral library signature for those type of rocks. So they have been left unclassified. And this is also technique that is called material mapping, or in this case, we should say rock material mapping. And other applications, you can do the same, not only with rocks, soils, but also with vegetation. And that was done here. And with this, I think I will finish because I think the time is, oh my goodness, yeah. And I want to take some questions just here for those who want to learn more about geological mapping using remote sensing. I recommend these books or these articles. This is from a Canadian source. And then this one is from Australia. That's actually the Ministry of I think Energy. Also very nice. And then this article here is from the US Geological Survey. All right, I'm going to switch here. Let me see to see if I see any faces. Yeah, so I'm ready to, take any questions.
Yeah, there is some question here. First from Miss Jenian. She asked how accurate our interpretation if we only use digital elevation model for lineament mapping. If any, which image do you recommend us to use other than digital elevation model?
Okay, so well, digital elevation models, the information they contain is terrain. It's basically elevation, So the approach there is different because what I was showing you about the lineament mapping, it's based not on elevation. That's not the information it's really using. It's using color contrast. No? And so with digital elevation models, of course, this is another important source for lineament mapping. But you would probably need to use a GIS system to sort of create a shaded relief map, no? And play with the illumination angle and the topography to highlight certain variations. I'm planning the next couple of lectures to show you some of my own research examples, and there we're using a combination of digital elevation models together with radar images and also optical images to map lineaments. So today I didn't touch digital elevation models, but yes, you can also do that. And what was the other question, or did I miss something?
Yeah, there is some. This is from Mr. Ahmad Shauki. He asked about what kind of satellite image that is good for remote sensing mapping. It is only Landsat, or there is other satellite image that we can use to remote sensing mapping, especially
yes.
lithology, because I see that you from your presentation you explain about the lithology mapping, lithology map from the remote sensing mapping.
Yeah, so Landsat is not the only one. I mean, nowadays we have many more. Definitely, you know, for lithological mapping, because the lithology usually doesn't change so so quickly, right? You can use a sensor called Aster. It's no longer working, but it's freely available, and it has more bands, spectral bands than Landsat. So Aster is like the best one right now for geological mapping. In the near future, we should see more hyperspectral, satellite-borne hyperspectral sensors, also freely available. I know that the Germans are planning to launch, I think next year, hopefully, or maybe the following year, a sensor called NMAP. And that will have a spatial resolution of 30 by 30 meters, but many, many spectral bands, like I think almost 200 or something like that. So that will be the best best sensor for geological mapping. But yeah, right now you have Sentinel-2, you have radar Sentinel-1, freely available. You have Landsat. You have some experimental sensors like Hyperion, but Hyperion is no longer working. And you got, I mean, I'm talking about freely available sensors or data. What else you got? This is pretty much it, because others, the MODIS and so on, the spatial resolution is not so good.
Okay, next question from Ms. Anis Kurniasi. She asked about, can we enhance the quality of image of particular area which have a lot of cloud?
Well, clouds are a problem. Actually, we wanna remove the clouds, no? And the only way is to search for another image, maybe sometime later, where that area you're interested in mapping has no clouds. So search for images that have very few clouds. If you don't find it, open your search criteria in such a way that you can search for different times of the year. Also, the time of the year may help you. You know, for example, in Indonesia, I would go and search for summer, you know, the dry season period, because I know that the clouds probably are less, you know, and chances are I find a cloudless image. Yeah, clouds. If you have an image that has clouds and you really need to use that image, whatever is covered by clouds, you won't see anything under the cloud. So use a cloud mask and remove that area. I mean, don't, basically you can't use it. All right, any?
Yes, this is from Mr. Sinatria Diko. He asked about, as you can see that from your example so far showing case study in arid region with high number of exposed lithological aspect. For us as a geological student or researcher that facing some problem when doing some remote sensing in tropical area with high density of vegetation and low exposed area. And his question is, can we using some of your method that you explained before, lineament assessment, IHS, band rationing, using Landsat 7 or 8 for doing geological mapping in tropical region, and how far we can suggest or believe that the result represent the similarity with field condition.
Yeah, so tropical environment are a challenge, but I think I mentioned that also last time. Even arid environments like Egypt may be a challenge in the desert, because the problem with the deserts is that you have this wind-blown sand covering the ancient fluvial surface. The ancient fluvial surface, because the deserts were not always deserts, right? So under the sand dunes, you have the fluvial landscape, but you cannot see it because you have all these sand dunes. And yes, in tropical environments, the same. You have the clouds and vegetation. So with the vegetation, it's similar like with the rivers. Rivers and streams, they tend to take advantage of weakness zones in the earth crust, right? In the landscape. They tend to follow a fault system and so on. So in vegetation, the same. They may also align along. I mean, I'm talking about the natural vegetation, not the agriculture areas. So that's different. But they may, show some variation. Maybe the tree heights may vary where there's more, moisture accumulation along, the natural channels, drainage channels, or maybe the vegetation that grows on limestone may be different from vegetation that grows over sandstone, or different from vegetation that grows over granites and so on. So that's why field reconnaissance and field validation is so important, because you may also want to look at even though you're a geologist, may want to look at the type of vegetation, type of trees or plants, the height, right? The density, all that may give you some clues of what's under the tree canopy, or, the best for all these for interpreting an image and so on, is to also have maybe someone who knows more about biophysical characteristics of the landscape take a look at it. Maybe you have a colleague or friend who knows something about a biologist who knows something about plants and may give you some information about the distribution of plants, and which type of soil they like to grow, and then maybe this serves to sort of understand what's the lithology. In terms of data fusion and so on, radar has the advantage of penetrating also the canopy a little bit, but unfortunately, pulsar data is actually pulsar data, which is the Japanese radar system, is now freely available for the old pulsar And so you may want to look into that. Pulsar 2 is not freely available, but Pulsar 1, the first one, is freely available. Explore that and see if you can use that to fuse Pulsar images, L-band images with Landsat or Sentinel. Well, with Landsat because it's Pulsar, I think, stopped working in 2011. So, and Sentinel was not around in 2011. So yeah, explore data fusion and just learn about vegetation and vegetation patterns and how that relates to geological or geomorphological landforms.
Okay, the next question is very interesting from Mr. Dimas. What is the best method to see lineament from LiDAR to know geological structures such as flood, holding, and fault for increase our accuracy of coal modeling?
Yeah, so LiDAR is it's an active sensor similar to radar, and LiDAR it depends which LiDAR system has the capability, well, of course, of penetrating the canopy, no, and reveal what's under the canopy, and you can create a very detailed digital elevation model using LiDAR. So for LiDAR, you need to use a specific software. Not every GIS system can manipulate LiDAR or image processing. And well, it's there to create a very detailed surface, terrain model, and based on that, then of course you can map the lineaments similar to to the examples I gave you with the different filters, the directional filters, and so on. Very similar. So once you have the surface topography, which is one band, one grayscale band, but instead of showing reflectance values, it shows differences in elevation, but it uses the gray shade. Can use the gray shade palette. You just run a spatial filter, a kernel, and highlight these variations. So in terms of topography, and usually lineaments, they show up either as ridges or short, incisions in the ground, and you can use similar spatial filtering algorithms.
Okay, the next question is from Rahmat Darmawan. He asked about what software should he use first as the beginner, and is there any minimum requirement for the PC or laptop for the remote sensing software?
Yeah, I think for beginners, I don't know if you are familiar with GIS, QGIS. It has some modules, user contributed some modules, and it's freely available, and there are some tutorials. If I can share my screen, maybe I can show you quickly what I mean. Sorry. Let me get the web page here. Okay, so QGIS. So if you go here, this is an open source software. No, you can download it, and you will see that besides of what comes with the GIS system, there is also something called SCP plugin, and the plugin, this one here, stands for Semi-Automatic Classification Plugin for GIS. And so it will provide you with, well, the plugin that you can download, but also with tutorials, right? And these tutorials are really good because they contain, you know, these videos, and there's a manual. And if you look at tutorials, it walks you through many types of operations, not only classification, but, you know, I mean, it's a very rich source. I would say for beginners, you may want to first go and use QGIS. The other possibility is, so videos are here. See, YouTube videos. So an introduction into classification, and you know, a land cover classification using Landsat and so on. It's mostly classification, but I think also sharpening and fusion is also, you know, listed here. And the other one, I would say, the other source, important source, is the Sentinel toolbox. Sentinel tool, and that's from the European Space Agency. And here you will find the toolbox for Sentinel-1, which is radar, for Sentinel-2, which is optical. And the other ones are for other type of sensors, but mostly for those that are interested in ocean applications, atmospheric applications. So for geologists, I would say Sentinel-1 and Sentinel-2. And again, you see the tutorials and, you know, videos, and, you know, I would start with either one or both, Sentinel toolbox and QGIS first. In terms of space, yes, you know, if you're going to process radar, you really need enough RAM memory, you know, the processing speed, you know, your CPU and GPU would be good. Optical, less. You don't need so much resources, you know, computing resources. But with Sentinel-1, which is radar, you need computing resources. And then, of course, you can also learn some image processing using Google Earth Engine, and that's cloud computing. And there, what you need is you need a good internet connection. So the examples I was giving you, Sentinel Toolbox and QGIS, the advantage is that once you download the software into your computer, you don't need to rely on internet connection, because, you know, it's a standalone software that resides in your PC, and then you can, but you need space, you need an external disk, you need, yeah. And RAM memory, I mean, minimum 8. I mean, if possible, more than 8.
Okay, I think this is the last question from Mr. Dafa Arofi. He had ever used unsupervised spectral angle mapping method, but he still have questioning about is there is any kind of metric or method that show about the precision of the analysis.
Yeah. So you mean the accuracy assessment,
yeah.
right?
Yeah.
Yes.
Yeah.
Yeah. Well, with any classification at the end, an accuracy assessment needs to be done. And so you also with spectral angle mapping method. If you don't have field information, you know, meaning that you go with your GPS to the field, your output, your classification output, and your GPS, and you go and check certain points and see whether what the spectral angle mapper you know, identified on the image is really there. If you don't have a way of doing it in the field, especially now with COVID. Another way is, of course, using Google Earth, high resolution images. But with Google Earth images, you need to make sure that the image you're looking at is approximately, the same time or year, or matches the year of the image that you processed and classified. For rocks and so on, it's not so critical because they don't tend to change so quickly. But for vegetation, this is critical. The season is critical and all that. So either visual interpretation of a high resolution image, Google Earth, for example, or you can go to the field, or you have maybe an accurate map for just a section of your classified image, but you can validate the information using that accurate map covering just a section of the image, and then extrapolate that information sort of for the rest. So that's called the classification accuracy assessment. And there are also tutorials. If you visit these sites that I just showed you, look for a tutorial that explains you how to run a classification accuracy assessment. That's very, very important. So that's a good question.
Okay.
Actually, I'm happy to hear that there are so many questions.
Okay, thank you. I think that's the last question. So this is the end of the course, I think. So before
the lecture, no? Today's lecture.
Yeah, the lecturer today.
Wait for a second.
Okay.
Bu Devina.
Yes, Pak Najib.
Yeah, Prof. Magaly. Yeah, Prof. Magaly. You know that many questions about how we can use about the remote sensing in the pandemic. You know that we got the problem with this situation.
Can you repeat in where?
In pandemic. Yeah, in pandemic COVID-19, you know that we mostly we can go to the field because we have many restrictions to go to the field.
Yes.
So you know that this year, a student should be conduct to practice about the field mapping, geological field mapping. But the problem is, like I told you, that many restrictions to go to the field. So that's why many questions about how we can use for using like that radar and then for the Landsat. But the question is, what is the simple way, or maybe just with the maybe a lack of data? I mean that we can in geological engineering department we don't have many resources about the data like a Landsat and then for the radar. But what the kind of data that it's maybe useful to go to the I mean that we can mapping the field without we go to the field, because it's only using the data from the remote sensing, so we can collect the data and then we can mapping. But maybe we can take some data from the field, maybe just only comparing or maybe ground check. So that's why we need you to explain maybe in the next webinar, so you can show us about maybe the simple investigation using remote sensing, maybe dam and digital elevation model, and then another simple remote sensing, so we can practice this year for field mapping, and then using not so many high technology for the remote sensing. Yeah, that's my actually not question, but actually we need you to give us about the information about how we mapping technique with a remote sensing, but with the simple, maybe not high technology, because we are lack of the data. So you can give us about that information. Thank you.
Yes. Well, the data is
Can you
actually
get yeah.
the data is actually available for free. It's not you know, it's and you can use, if you don't have the resources, you know, to download it. So one way is to use cloud computing, which is Google Earth Engine. You know? You can also use geodata portals to visualize the information. You know? And but the thing of these geodata portals, when you, like Google Earth, for example, no? The problem is that there are no coordinates. No, so Google Earth is very good because you zoom in and you see all kinds of details, but you don't have spectral information, no, and you don't have the coordinates. So I mean, somehow you know the location, but you know. Somehow you need to use a software, either a GIS software or an image processing. Or the other possibility is you use an image that was already processed by someone, and it has coordinates, you know, like a map, right? But yeah, it's going to be difficult to rely only on someone else's product. I think some of the questions I see here, that some people are using DMs already, and I suppose that they're using a software. So you can start with a DM. That's not a problem. And I would say a GIS system, you know. But in addition to the DM, also use the plugin, the one that I showed you, or download an image and use that together with the Landsat. So next time I'm going to give some examples of how we carry out, you know, geological mapping. And I'm going to talk less about the techniques. So I just covered some fundamental aspects to prepare students for the application. No, but
yes, that's good.
But I think that if students start now looking into the GIS, the QGIS, for example, you know, the tutorials are really very, very nice. And at some point you need the software, because if you don't use your own software to manipulate the images, then you need to rely on someone else's images. And chances are that maybe for your region, there are no images, usable images, already processed and analyzed. No? So it's going to be difficult.
Yeah, thank you. Yes, maybe next week you can also show me how to proceed, and then about an example, so we can for the student this year can practice, and then for mapping geology.
Right. One thing I can do is, because I have some exercises that I wrote for QGIS, no, for quantum GIS, and I can share those exercises before my talk. I can share with you the
that's good.
material, and then you can ask some of your students to first install QGIS on their computer laptops, no, and then see. I will also provide you the Landsat data. You know, I will put it on the website so you can download it, or your students can download it. You just share the link, and they need to install QGIS. And I will also provide you an installation guidance, what plugins they need to install. And then they need to download the data and the exercise, and then see how it goes. We can do that.
Okay. Thank you.
Just to see if how comfortable they are with the tools. But you need, as a geologist, you need to learn a tool. You cannot only rely on pictures that someone else produced, because chances are that for your study area, no one has actually looked into processing the images the way you need them. You need to do it.
Okay.
It's not
Okay,
so
thank you,
difficult.
Prof. Magaly.
Okay.
Yeah.
Okay, is there any else want to ask Professor Magaly? Okay, I think it's enough. It's 2 hours more from Professor Magaly this session. In closing, before closing, I will read the conclusion, a little bit conclusion. So from this remote mapping technique using remote sensing, first we have to enhance the image, and for enhance the image, we have data fusion and then spatial filtering and so on, like Professor Magaly first explained. And then we can use software like NV. Is it true,
Yes,
Professor Magaly?
the software. Yes,
Yeah.
the image processing software.
Yeah. And then for the open source, we can use QGIS. So, and for the next lecturer, maybe you can explain to us about the QGIS and the
Yes.
okay. Thank you for tonight. Before we close, can we get a photo session together for our participant? Can you open up your camera so we can take a photo together with Professor Magaly? Turn on the camera, please.
This way I get to see the faces. That's nice to see all the faces.
Okay, Mas ready? Are you or still here?
Yes, I'm here. Wait a minute. Should we take all the participant or just first page?
I think first bit is enough.
Okay. Okay, then I'm done. I'm finished.
Okay. Thank you, Mas Heidi. Thank you, Professor Magaly, for today. Next time we have class again, and see you to the next class.
Okay.
Good night.
Night. Well, for me, it's good morning.
Oh yeah, sorry. Good morning.
Good morning for you.
Good morning, good night. Bye-bye. And
Bye.
Najib, I will email you. I will get in touch with you,
Okay.
Najib. Okay? We'll
Okay.
figure out a way. Bye-bye. And
Thank you. Okay. Bye.
Pina,
Okay.
many thanks
Thank
for
you,
monitoring,
Thank you
moderating.
so much.
Bye-bye.
Bye.
Bye.
Terima kasih partisipasinya untuk malam ini kepada para peserta. Mungkin minggu depan kita akan latihan langsung menggunakan GIS. Silahkan untuk meninggalkan ruang dan menikmati istirahat malamnya.
Mbak Devina.
Iya, Mas. Gimana?
Kita udah 2 jam 14 menit, udah cukup ya berarti ya?
Cukup banget. Udah more banget.
End stream ya, sama stop record ya? Oke.
Di close aja nggak apa-apa Mas ini, itunya.
Terima kasih semuanya, saya keluar, dadah, saya tutup meetingnya.
Saya
Ki,
juga.
di mute Ki, punyamu Ki. Ciao.